Welcome to Chemistry 312. Continue where we left off. As promised, we will focus on the Diels Alder reaction. It is a reaction of combination of 4 pi electrons with 2 pi electrons to form a six-membered ring and 2 pi electrons. It's called a 4 plus 2 cycloaddition. Now, this is a concerted reaction that adds a adds an ion, what no, a diene, what we concerted addition to from a diene to what we call a dienophile. A dienophile typically is an alkene or alkyne with electron withdrawing properties. So just like a electrophile is a atom, some sort of atom that has electropositive properties, thus wanting electron density. A dienophile is a diene, what is a alkene, or essentially a pi bonded structure that has electron density being withdrawn from it, thus designing the electron density from a diene. So the reaction looks essentially like this. Start. Oh, bond. So diene. So make it as pretty as I can. Plus a dienophile. And this W is a withdrawing group. So what we have here is the electrons from this swing over, attack this carbon down here. Electrons here will swing up and attack that carbon there, and the electrons here will then shift down to form that center piece. So the resulting product is a six-membered ring. We have the withdrawing group right there, and we've now made a double bond here. So we have 2 new single bonds connecting the diene to the dienophile, and we've shifted down the alkene. Now, if you did this with a alkyne, so said go triple bond with the withdrawing group. Okay, the sterically, the same thing would happen, except we only break down one of the pi bonds there. So we keep one of the pi bonds. So either way, all of our dienes should be electron rich with like uh, uh like R, like alkyl group or a methoxy group, essentially things that have a lot of electron density, aren't too electron withdrawing, can donate some electrons into the ring if need be. And the dienophile should be electron poor. So we want electron withdrawing groups like aldehydes, that's a good one, aldehydes and ketones, or cyano groups. Cyano group is the CN with the strong electron withdrawing from the nitrogen. So aldehydes and nitriles typically for the dienophile, and electron rich dienes like just an alkyl group or a alkoxy group. Now, stereochemistry is going to be real key, so we got to watch out as we do this. The diene must be in S-cis formation, where they're both on the same phase. We can't have. We can only use this. We cannot use. Oh shoot! Screw that up. We cannot use the S trans. So we cannot use that formation because of the way this must work in order to form that six-membered ring. So this is because we essentially need the p orbital overlap, as the diene sits on the p orbitals of the dienophile. So we need essentially the overlap between the 1 and the 4 p orbitals. If I call this 1, that being 4, we're going to have that sitting down on the pi bonds between the dienophile. And so in this case, 1 is here and 4 is there. The diene is not going to have overlap. Anything that hinders this S-cis conformation will hinder Diels Alder. So if I have a bulky alkyl group, it's going to keep this from going. So like here's a couple examples of dienes and the reactivities. So, so diene. No, okay, sorry, wrong thing. Diene. Yeah. I need a, okay. Boom, boom. This will not happen. This one will not react at all. No Diels Alder. Yeah. Let's see. Okay, put in this. Having a stereochemistry like this is going to hinder that. It's going to hinder this. If I put up this methyl, because that's going to block the overlap. A better version would be methyls like that. Even better version would be, I'm going to erase this. Even better version would be like this. And one of the best ones is a cyclopentadiene. Part of this is because it holds this in the cis. It's very reactive. However, this will dimerize. So one of the problems with cyclopentadiene is it will Diels Alder with itself. It's because this holds it in the cis conformation. So let's put that boom, boom. Let's show the dimerization real quick. Okay. So there is the diene, the dienophile. Boom, boom. So once again, swings over here, swings over there, swings down. So draw a six-membered ring. The double bond there. However, because bicyclic and because this is also a ring, so this dimerizes like so. So we have really a tricycle. We have the bicycle in here, and well, not really a tricycle, but a bicyclic ring here connected to another ring. So it is a hot mess. But let's see. This will always result in the syn stereochemistry. This is going to be the addition to the same side. So the dienophile will either add to the top face or the bottom face of the diene. However, so the stereochemistry of your dienophile is going to relate to the stereochemistry of your resulting 4 plus 2 product. So let's take a look at this in the simplest form. If I have this basic diene and I have a cis dienophile, So since it's going to attack from the top side or the bottom side of the 6-membered ring, and there's no other stereochemistry on this ring, we can have either this product, or we set down on the top, or, well, and or really, because we're going to get a mixture of both of these, especially if there's no preference. Of that product. So we either have both of them going up or both of them going down. So the same way, if I instead, let's erase this real quick. Instead, I make this guy into a trans. You're going to have a mixture of products again. This time you're going to have one going up and one going down because it's sat down on the face and they keep the stereochemistry. And you're going to, of course, get the other isomer. Now, right now, you could say, oh, that's fully rotatable. You can, this has a symmetric axis. This has a rotational axis right there. So in both those cases, you could rotate this 180 degrees along that axis and get the two isomers. So, well, actually, no. No. No, you can't. Those are two separate isomers. So, oh. But at least in the previous one, you could rotate it and get the two different isomers. But however, anything that keeps that if you have an unsymmetrical diene, that will definitely play a role in the products, as we'll see in a minute. However, let's look at this. So let's say now, erase that, pretty that up. I'm going to leave those in there for now, so it's going to make it a little bit easier drawing later. So now, what if I suddenly change how my diene looks? And I'm going to, in order to keep this simplified as possible. So these guys no longer have isomers because of the double bond. But if this sits down on top, it's going to push those down. If it sits down, if it attacks from the bottom, it's going to push those up. Basically, your stereochemistry is going to be dependent on which side attack. So you're always going to have two isomers from this, depending on attack from the top, attack from the bottom. So keep that in mind. However, there's a rule called the endo rule. This is a big important rule when we think about it. Endo rule. The electron withdrawing group of the dienophile will have a secondary overlap with the C2, C3 position of the diene, forcing the electron withdrawing group into the endo position. So if I have a bicycle, for example, the electron, so if I have a bicycle here, okay, let's I'm going to save myself a little bit of trouble. Let's go just erase this so we can see this. The endo rule. No, not text. Draw this. Okay. I'm going to put CHO as our aldehyde. The endo rule says we're going to have an overlap between the C overlap of this guy with the C. If this is 1, this is 2, this is 3, this is 4. We're going to have an overlap between these two carbons and that. The pi cloud of there, meaning of the two possible ways of attack here, we're going to have, let's draw my bicycle. Okay, there's our 6-membered ring, all bent up. You have this possibility, Cho. That is the endo position. You also have endo. You could also have bicycle. You could also have this, also in the endo. But you will not have the exo, which would be this. One of these includes this. You will not have that. So this one is coming away from this ring, kind of moving away. This one is kind of tucked under the ring so that the aldehyde can interact with this pi cloud down here. It can interact under the ring. It's kind of, the endo is kind of tucked under the ring. Exo is kind of pointing out of the ring. You would think the exo would be preferred because the exo is the least sterically hindered. You're not trying to tuck a big bulky group into a little pocket. You're allowing it to float freely. However, there is an interaction between the pi cloud of the withdrawing group and the pi cloud of this C2C3 alkene that is preferential. So the endo rule, as I said, the electron withdrawing group will always try to be endo with the dienophile. So it's going to adopt an endo substitution whenever possible. So now, in an unsubstituted Diels Alder, typically one product is favored over another. And this is going to put the negative charge in the diene with the positive charge of the dienophile. So just a quick look. So if I have, I'm going to put just a group D right here, a donating group, and a group W. You could hypothetically, regardless of enantiomers, you could imagine two different possibilities. 4 if you include all the enantiomers. So you can imagine this guy, W. I put a squiggly so we say no, it's like a enantiomer. And you can imagine this guy. Sorry, squiggly. This guy would be called the 1, 4, and this is the 1, 3. Counting from the diene, 1, 2, 3, 4, kind of from the diene the donating group 1, 2, 3. So what happens, you actually, in this situation, you get a 1, 4. That's the only one that forms. In the case of your diene where you have the D donating group on the 1 position and it right there on the end, and your withdrawing group, you could have 2 possibilities. You could get say a squiggly D, squiggly W. This would be the 1, 2. And you could get squiggly D, squiggly W, the 1, 3. Once again, we get the 1, 2, not the 1, 3. You get the 1, 2, not the 1, 3. And that's going to have to do with this charge. So let's imagine this. As we're pushing electrons, let's look at this. So the electron withdrawing group is the easiest to imagine because, I mean, essentially what we're looking at is electron pushing. That if the donating group donates electrons to make the double bond, where we're going to kick this out. We're going to kick this out here to make a negative charge. And so the resonance structure here with a donating group in the 2/3 position is this. D minus. Now, with the withdrawing group, the resonance structure is always going to be the same. That withdrawing group, electron density is pulling up into here. So the resonance structure puts the positive charge down here. So that diene always wants to attack down here. So as I said, the negative charge always wants to be attracted to the positive charge. So let's do that connection. Boom. So if this is partially negative, put the W there. That's partially positive. They're going to want to align. So where's that at? 1, 2, 3, 4. Let's erase that again and do it from the other perspective. Okay. If I put the diene instead right here and say the electron's going to swing here, swing over, swing up. So the resonance structure there instead has negative farthest away. But the negative and the positive, we have that in mind. D partial negative, partial positive. Putting those bonds together, 1, 2. So naturally, we're going to want to adopt the 1, 2 position or the 1, 4 position, depending on whether the donating group is in the 1, 4 or the 2, 3. but we're not going to want to form the 1,3 diene of Diels Alder. Okay. Now, we're going to bring this all back to our stupid MO diagrams. I know MO is hard. MO is difficult to imagine, and you have to kind of review this stuff, but it's how this works. It all works MO, molecular orbital overlap of these p orbitals. This Diels Alder is what we call a pericyclic reaction, a concerted forming and breaking of bonds within a closed ring of interacting orbitals. There's a conservation of orbital symmetry. So the molecular orbital of the reactants must flow smoothly into the molecular orbital of the products without a drastic change. These are also called the Woodward-Hoffmann rules. So let's look at the 4 different pi molecular orbitals of our diene and the 4 different pi molecular orbitals of our dienophile. So draw them. And then our shoot. There's a boom. Molecular orbitals. So actually, can I stamp? Shoot. Okay. Oh, there we go. Can I do this? Yeah. MO. I'm trying to draw in our pi orbitals real quick. At least the shaded part. I'll see about the unshaded part in a minute. Mm-hmm. So we have the all no nodes bottom orbital and the no nodes and the all nodes top orbital and 1 node and 2 nodes in between. Mm-hmm. Okay, let's see if I can draw. There we go. Save me a little bit of trouble. Okay. Oh, for God's sake. Okay, try that again. It's my own fault for putting them too darn close to each other. Try that again. So remember, the 2 orbitals have to be in the same phase to have an overlap. So we have on the lowest energy orbital is they all overlap. The highest energy orbital is no overlap. So that's our anti-bonding. Okay, let's go back to drawing. Okay. So in this one, we have 4 electrons. So we pair 1, 2, 3, 4. This is called, and this one we have 2 electrons. We have only this one, the highest energy orbital that is filled is called the HOMO, the highest occupied molecular orbital. The HOMO. This one is our HOMO. The next orbital up is called the LUMO, our lowest unoccupied molecular orbital. So all chemistry involving electron pushing will actually come back to this homo-lumo concept. The electrons have to go somewhere. And so the electrons, as they're being transferred, are being transferred from the homo into the lumo, somewhere else. When we're looking at metals and all that, we're looking at where these molecular orbitals. You're looking at electron excitation. It's being excited into usually the lowest unoccupied molecular orbital. So what's going to happen in these situations is the HOMO of our diene is going to donate to the LUMO of our dienophile. So the HOMO right here, this second structure, is going to donate to the LUMO right here of this structure. So we are going to have a sitting down. So let's look at that. I'm going to redraw this. Let's see. I'm going to try to, wish I could cut this out, but I'll just clear all. You know, I just spent, seems like forever on that. So, hold on. Yeah, it took too long to stamp everything. Go back to my crappy drawings. So there's the HOMO of our diene. It's sitting down on the LUMO of our dienophile. See that whatever this pi cloud is, this pi cloud, that this is interacting here. This is interacting there. That this is symmetry allowed. That essentially this is smoothly, this is shifting over. Which is down overload. Now, this also explains why we don't see this with a 2+2 addition. We don't see this with a 2+2. We do not see this reaction. We see a 4+2, but no 2+2 will not equal our. We're not going to equal this. Because in the homo to lumo of that situation, we look at. We look at the homo versus the lumo. See, this may be able to interact, but this cannot. And we're like, well, why don't you put homo to homo? Well, you can't do that because the electron is already occupied. The orbital is already occupied. So this is symmetry forbidden. This does not occur. At least it does not occur as a concerted mechanism. It could happen as a two-step, but it could not happen as a one-step, at least as written. Now, you can make this occur through what's called photochemical induction. So in the photochemical induction, you're essentially saying you're taking the homo and the lumo. Oh God, this is annoying. Homo, lumo of here, and you're using light. You're artificially exciting one of the electrons into the lumo. So thus allowing potential overlap. So if I use light, so I can then donate from homo into homo. Well, I can donate from, we have an empty space that we can now put the electrons into. So 2+2 cycloaddition is allowed photochemically, but thermally it is forbidden. So we cannot do that. But essentially, what are you doing? You're exciting. Oh, you're exciting both of them into the LUMO, which then says, "Oh, okay, I can do this now." Okay, so now we see overlap. If both of the alkenes are are in the pi star orbital, we can now see the overlap. Now, at this point, I would normally talk about UV spectroscopy, but it's I'll spend a little bit of time. I didn't normally teach this, but I'll go ahead and go over this just to finish up this chapter. UV absorption spectroscopy detects essentially electron transitions between these conjugated systems. That the ultraviolet wavelength is between 200 and 400 nanometers. This can be detected in the infrared. It's not very easy. It's like two or more absorptions, two or more double bonds. It becomes very difficult. Our possible UV visible is between 200 and 800 nanometers. In ultraviolet, our sigma bonds are very stable, but the pi bonds are delocalized and thus far easier to move. And what we're going to see is our excitations from HOMO to LUMO orbitals. Now, for example, ethylene. Ethylene has a absorption of 171 nanometers, but butadiene is 217. And one of the things is the longer the conjugation we have, the longer the wavelength it needs for absorption. So when we look at isolated alkenes do not count. So if I had boom, it's still going to be like 171. They do not add. But in UV-vis spectroscopy, we're going to have a reference cell and our sample cell. The reference cell is going to essentially measure and cancel out, figure out what is the water absorb, what is our solvent absorb, whatever, something to compare the absorption to, so we know exactly just what our sample is. We're going to use a monochromator that's going to essentially produce just single wavelengths at a time, and it's going to work based on the Beer's law, the whole idea that the absorbance is equal to the log of the incident light of the reference over the incident light of the sample, and that's going to be related to the molar absorptivity, the path length, and the concentration. Now, the wavelength of the max absorbance is going to be our lambda max, and the value of your molar absorptivity of sigma right there is the molar absorptivity at each maximum. And basically, there are certain bases like transalkene. Well, actually, butadienes have 217. Let's see, uh, like this structure, the the hexadiene is 256, and with two internal ones, and one with a mixed internal and external as 232. And from there, using one of these three base structures, there's a whole list of numbers and measurements that you can modify this to calculate the expected uh, absorption. So you can kind of tell where our double bonds are and how many double bonds. Each alkyl substitution will onto these along these double bonds will add 5 nanometers. Each conjugated bond will add between 30 and 40 nanometers to the ring system. So you have 217. If I put, like, say, methyl there, that might add 5, and so that becomes 222. If I add another one, maybe it's going to become what? 227. And so you can kind of figure out what your structure looks like. And just a quick reminder, color appears due to the absorption of the opposite color. So if your solution is colored of any type, it's absorbing the antagonist color. So Roy G. Biv, red, orange, yellow, green, blue, violet. So if it absorbs yellow, it would appear violet, and so on. But I'm not going to focus on that too much because that is the end of the chapter, and that's not something I particularly use very much. But in case you go over it, that's just a quick intro. Thank you.